Hello everyone. Today we will talk about inter-process communication or IPC. IPC refers to the various ways in which processes talk to each other. So why would processes need to talk to each other? Because to do anything useful, any process needs to interact with rest of the computing system, including other processes running on the same machine. Some simple forms of inter-process communication. First, let's look at some simple IPC mechanisms. We are already familiar with some of these. When we learned about fork and exec mechanism for manipulating processes, we also encountered system calls wait PID, and exit. These system calls provided a rudimentary mechanism by which a parent process and a child process can talk to each other. When a child process terminates, it can communicate its exit status through the argument for the exit system call. This exit status is then delivered to the parent through the wait or wait PID system call. Next, processes can also talk to each other by reading or writing a common file to the disk. Some multiprocess applications, such as a web server, may write the process ID of the main process to a PID file. This file can be read by others to send a signal to the application or to prevent starting another instance of the same application. For example, you may not want to start two instances of the same web server on a common machine. Signals are a simple notification mechanism. One process can signal another process that some event has occurred. Sometimes, even the operating system can signal an event to a process, for example, to kill or to stop a process. Other types of IPC mechanisms include shared memory, semaphore, pipes, and sockets. We will discuss pipes and shared memory in more detail later in this lecture. Semaphores are a type of inter-process synchronization mechanism. They are not used to transfer data. Rather, they allow processes to synchronize with each other upon certain conditions, such as locking or unlocking shared resources. We will discuss semaphores under the topic of concurrency. Sockets are used to exchange data between processes in a bidirectional manner. Bidirectional means that a process can either send or receive data using the same socket. Sockets are commonly used to communicate between processes on different machines. However, processes on the same machine can also use certain types of sockets called Unix domain sockets to talk to each other. We will not discuss sockets further in this course, but if you are interested, feel free to ask me for more information. So now let's talk about pipes, which provide unidirectional communication between two processes. As the name suggests, a pipe provides one-way flow of data from one process to another process. Much like a physical pipe carries a water from one end to another. A pipe is created. Once a pipe is created, one process can write to one end of the pipe and another process can read from another end of the pipe. You create a pipe using the pipe system call, which takes no arguments but returns two file descriptors. One file descriptor, shown here as FD0, represents the read end of the pipe. Another file descriptor, shown here as FD1, represents the write end of the pipe. So what exactly is a pipe in terms of implementation? When you call the pipe system call, the operating system sets aside a buffer or a piece of kernel memory. This kernel memory is used to implement a first in, first out or FIFO data structure. A pipe provides a byte stream abstraction for communication, which means that there are no explicit message boundaries. For example, the writer can write 10 bytes at a time, but the reader can first read 5 bytes, then read 15, then read 15 again, and then 5. Or the reader and the writer can choose any other byte boundaries to read or write from the pipe. In contrast, message abstraction specifies explicit message exchanges. In the above example, using message abstraction, the reader would have to read 10 bytes at a time, each read being one message. To use pipes, two processes must be related to each other by either a parent-child relationship or they must be siblings of the same parent. This may sound confusing, but let's look at a simple example. Here, a parent process first creates a pipe using the pipe system call. This gives us two file descriptors, one for the read end of the pipe and another for the write end. Now, the parent process forks a child process. Remember that fork creates an exact replica of the parent process in the child. So the child inherits any open file descriptors from the parent. Thus the child also inherits the open pipe descriptors from the parent. In this picture, the parent and the child now have identical references to a common pipe through which they can talk to each other. Next, we need to decide who writes to a pipe and who reads from a pipe. Remember that the pipe is unidirectional, so the parent and the child need to agree in advance on the direction in which data will flow. In this example, the child wants to write some data into the pipe and the parent wants to read some data from it. Hence the child closes FD0, which represents the read end of the pipe, because the child doesn't want to read from the pipe. And the parent closes FD1, which represents the write end of the pipe, because the parent doesn't want to read from the pipe. Now the child can write data through FD1 and the parent can read data through FD0. So you have a unidirectional pipe from the child to the parent. Now what if the parent wants to send data to the child? The parent would need to open a second pipe before fork, and then the parent and the child would need to close the complementary file descriptors from the above example. You may wonder why the parent has to open another pipe for bidirectional communication. Why can't the parent use the same pipe to send data to the child? After all, the parent has access to FD1, correct? Remember, the pipe is a byte stream abstraction, which means that there are no message boundaries. If parent and child write to the same pipe, their data can get mixed up. So the parent and the child can end up reading what they themselves wrote into the pipe. It will get too complicated for the parent and child to keep track of who wrote what bytes. It's just simpler to use two different pipes. Here is another example of a command line shell that uses pipe to communicate between two commands. Such input-output redirection is also called a filter in Unix. In this example, we want to redirect the output of the ps command to the input of the less command. The ps command lists the processes running in a system. The less command formats the input and displays it one screen at a time. This figure shows one way of doing this using a pipe. The parent shell creates a pipe and then forks two child processes. Both processes inherit the pipe descriptors to a common pipe. One process execs the ps command and another process execs the less command. Since exec retains open file descriptors, the pipe descriptors remain open in the exec processed images. The ps process then writes to the pipe using fd1 and the less process reads from the pipe using fd0. Make sure you try this example by running the code given in the link. Try to change the code to execute different commands. If you want the shell to execute a filter chain of arbitrary length, then you might find it easier to implement a recursive program to do so. Except that the recursion is done through the exec system call instead of the normal function-based recursion. There is an important detail in the code from the last slide about how to redirect the standard input-output from or to a pipe. This is done through the dupe2 system call, which copies one file descriptor reference to another. To understand what this means, consider the file descriptor table of a process. File descriptor table is an array maintained by the operating system for each process. Each entry in this table refers to an open file or device or IPC object, such as a pipe. Descriptor 0 refers to the standard input, which is by default the keyboard. Descriptor 1 refers to the standard output, which is by default the screen. Sometimes, as in the case of pipes, we want to change the input and output to point to some other descriptors, such as pipe descriptors. The code in the previous slide shows how dupe2 system call makes standard input refer to the read end of the pipe and the standard output refer to the write end of the pipe. Dupe2 closes the file referred to by the second argument if it was open previously. Another legacy system called dupe did not perform the close, so the programmers had to do so explicitly. You may want to refer to the man pages for dupe2 and dupe. This slide shows a rough approach for implementing a recursive version of the filter program that we discussed earlier. I leave out the details for you to figure out. Of course, feel free to ask me or the TAs if you get stuck. With byte-stream abstraction, you want to be careful about using the read and write system calls. Remember that read system call may not return the number of bytes you expect to read. For example, you may want to read 6 bytes, but only 4 bytes may be available at that instant. So the read system call may return with only 4 bytes. The return value of the read system call indicates how many bytes were actually read. If you don't check the return value, you might mistakenly assume that 6 bytes were read when only 4 were. Similarly, the write system call may write fewer bytes than you wanted to write. Can you guess why that is, why would the write system call write fewer bytes than you ask for? It is the programmer's responsibility to check the return values of read and write system calls and to invoke them again to transfer the missed bytes. A corollary of this discussion is that by default, read system call would block the calling process if there are no bytes to read from the pipe. If you can, of course, change the behavior of the file descriptor to be non-blocking, which means that the read system call would return 0 if there was nothing to be read right away. Here is some sample code that shows how to repeatedly invoke the write system call till the desired number of bytes have been written. You can construct a similar function to repeatedly invoke the read system call until the desired number of bytes have been read. Next, we will discuss a powerful IPC mechanism called shared memory. Shared memory allows multiple processes to exchange data without invoking the read or write system calls. As with pipes or sockets, exchanging data using shared memory is as simple as accessing your own memory. But this increased convenience also comes with some pitfalls. Let's take a look at how shared memory works. In this example, process 1 creates a piece of shared memory using a create operation. This requests the operating system to set aside a buffer of the requested size. Each shared memory has a unique name, referred by a numeric key. Other processes can use the numeric key to access the shared memory. Any process which wants to communicate via the shared memory uses the attach operation with the unique name or the key given by the creating process. The attach operation maps the shared memory to part of the virtual address space of the process. In this example, 5 processes have attached to the shared memory to their address space. After attaching, each process can read or write to the shared memory region as if they read or write to their own memory. There is no need for any system calls. The attach operation returns a pointer which refers to the base virtual address of the mapped memory region. This is very similar to how malloc works. You invoke malloc to ask for memory, and it returns a pointer that points to the first byte of the malloc memory. Similarly, the attach operation returns a pointer to the first block of byte of the shared memory. Remember, the same shared memory can be mapped to different parts of the address space of different processes. This means that the pointer value returned by attach can be different in each process, although the pointers point to the exact same memory region. This slide shows the system call used to create a shared memory. You create a shared memory using the SHM-get system call. The first argument is the unique name you want to give to the shared memory. Since the numeric key should be unique system-wide, programmers usually use the fork library function to generate a unique key. The programmers usually use the f2k library function to generate the unique key. The f2k function takes a file name and an additional character as argument and returns a system-wide unique key. Why do you give a file name to f2k? Because each file on the disk has a unique inode number which f2k can combine with the second argument to generate the key. What is an inode? You will find out later when we discuss file systems. Why does f2k take a second argument? so that you don't need to generate humongous number of files just to generate a unique set of keys for one application. You can simply use a different second argument to get a different unique key. The link in this slide points to a program that creates a shared memory and then the program dies. Note that the shared memory continues to exist even after the process which created it dies. Interesting, no? That way, another process can attach to the shared memory at some later time. This slide shows how to attach to a shared memory using SHM-get and how to detach from it using SHM-dt. This slide shows how to attach to a shared memory using SHM-AT and how to detach from it using SHM-dt. These are somewhat self-explanatory system calls. Attaching is done through a combination of SHM-get and SHM-AT system calls. The SHM-get system call returns a SHM-ID, which is similar to a file descriptor FD that we used earlier for pipes. When we pass SHM-ID to the SHM-AT system call to attach to the shared memory of the processor's virtual address space. The process detaches from shared memory once it is done using it. Note that detaching doesn't delete the shared memory, just like attaching doesn't create the shared memory. Detaching just tells the OS that this process is done using the shared memory. Why do they use two system calls to attach? Why doesn't SHM-get return the data pointer directly? Well, because you can use SHM-ID, which is returned by SHM-get, to do other things. Like for SHM-CTL system call that manipulates the shared memory. Just some confusing quirks in Unix. Try the program given in the link. It allows you to write to the shared memory if an argument is given. It also reads from the shared memory if no argument is given. This program shows how to delete a shared memory, which means get rid of it for good. Basically, we are telling the OS to destroy the shared memory completely. You delete a shared memory using SHM-CTL system call with ipcrmid command as argument. Try this program on a shared memory you created earlier and see how it works. IPCS is a command you can use to list all IPC objects in the kernel. Shared memory is also an IPC object. IPCRM allows you to delete an IPC object from command line. For example, an administrator can delete shared memory objects that have been left around by others. Next, we discuss signals, another type of inter-process communication mechanism. Signal is an event notification to a process. A signal could be generated by a process or it could be generated by the OS. But a signal is always delivered to a process. There are lots of different types of signals. You can list them all using the command kill-l. Kill is a legacy Unix terminology for delivering a signal to a process. It doesn't actually kill a process unless the signal type is SIGCHLD. Some signals are more commonly used than others. For example, SIGCHLD is delivered to a parent process when the child process dies. SIGKILL kills a process. SIGSTOP stops a process but doesn't kill it. When a signal is delivered, a process can either do something about it or do nothing. If a process does nothing, then usually the process is killed by the operating system. An exception is the SIGCHLD signal, which is ignored by default and the child continues to run. If a process chooses to do something about a signal, then it can install a signal handler using the SIGAction system call. Signal handler is a function that is invoked when a signal is delivered to a process. The process is interrupted by the signal. It pauses whatever it's doing, executes the signal handler function, and then resumes wherever it was paused before. A process can also ignore a signal without invoking a handler. But you cannot ignore SIGCHLD and SIGSTOP for obvious reasons. The OS needs these signals to maintain control over each process. Check out the examples in the link which show how to signal the SIG how to handle the SIGINT signal. The SIGINT signal is generated by Control C on the terminal. This slide gives some interesting information about SIGCHLD. The key point is that a signal handler for SIGCHLD must be installed before the parent calls fork. Other than that, you can figure out most of the other information from man pages. The program in this link shows how you can install a signal handler for SIGCHLD so that the parent process doesn't need to block on the wait system call. Instead, when the child dies, the signal handler is invoked, which can then call wait without the blocking behavior. One thing you may want to investigate on your own is how do signals behave when a process is in the middle of a system call. Does the system call get interrupted or does the system call get restarted? It turns out that different operating systems have different behavior. So you have to be mindful of operating system specific behaviors when you use signals, when you mix signals with system calls. You may also want to check out man pages and Google for Unix signals to get a ton of useful information. Finally, references. Richard Stevens' book is a great reference to learn about interprocess communication, but there may also be other books that are equally good. That's all we have about interprocess communication, folks.